Myself, Dr. Arti Malik, Assistant Professor in Applied Science Department from IMT College, Greater Noida. Today, I will discuss the inverse problem of epidemic models. First of all, I will discuss the inverse problem, a general introduction of inverse problem. Inverse problem is a vibrating branch of mathematics widely applied in other branches of science and engineering. It is a multidisciplinary in nature and broadly in image processing, signal processing, geophysics, astrology, and epidemics, and any other branch. Inverse problem are the opposite of the direct problems. In the direct problems, one find an effect from the cause, and beside that, in an inverse problem, one is given the effect and we wants to recover the cause. In terms of, we can describe it in terms of output and input. In direct problem, input is known and we have to find the output. While in inverse problem, the output is known and we have to find out the input, or that will be exact or at least approximately. Now, mathematically, we can show the direct problem and inverse problem. Let there are x and y be spaces having appropriate structure, maybe Banach space or Hilbert space, and the operator T be a operator describing the relationship between the data y and the model parameter x. The given that is denoted by t that x tends to y. The direct problem is that we have x and we have to find the value of y. But in inverse of problem, we have to find out the value of y if x is given. The given a desired output z, find an input x that procedure and output of y that is as close to at z is possible. That is given in the following format that is shown in the mathematically. Next, in other way, we can discuss the direct problem in an inverse problem. The question is, one question is that which is one of the best university in northern India? Then answer will be IIMT University is one of the best university in northern India. Again, the same question, which one of the best university in northern India? Answer will be IIMT University. This is the direct problem. But the in inverse problem, answer is known and we have to explore the question. The IIMT University is one of the best university in northern India. Then what will be the question? The question will be, which is one of the best university in northern India? Exactly same. If we will write the answer IIMT, then the question will be, there will be two questions, which is one of the best university in northern India. That is one question. Second question, write the name of the one write the name of one of the best university in northern India. Question 1 is well posed and question 2 is ill posed. Next, well posedness. In sense of Hedmard, a problem is well posed if three conditions are satisfied. First condition, the first condition is if the problem has the existence, yani ki if the problem solution of the problem is exist, you can say that that is existence property. The second property is if the solution is unique. This property is known as uniqueness property. And the third one is small changes in data produce small changes in output. That this property is known as the stability. Mathematically, we can show that we have discussed in previous example. Let x as that x tends to y be an operator, then for all y belongs to y and x belongs to x such that tx is equal to y. It means solution exists. This is the existence property. Uniqueness, if tx1 is equal to tx2, that will be possible when x1 is equal to x2. This is uniqueness property. Stability, for all x and a subset of x, then txn is equal to tx. This implies xn tends to x. Ill-posedness of a problem. If any above is not satisfied, then the problem, you can say that will be ill-posed. Solving an ill-posedness problem is much harder to solving the well-posedness problem. Most of the inverse problem are ill-posed. Uh, it means they are not satisfying the third condition of the uh, head mod. Hence, solving the inverse problem is a very difficult task. To overcome this difficulty, a term is added to the problem to make the problem solvable. This may be different types depend on the problem. This term is known as regularization term or function or penalty terms. The regularizer appears with the multiplication of a positive number generally denoted by lambda, and this lambda is known as the regularization parameter. A numerical example is also here. We first provide a numerical example to give the idea of well-posedness. Consider a n by n Hilbert matrix. Aij is equal to 1 upon I plus j minus 1. And the multiplication of matrix A and input of x that will give the output of x. For this example, we choose a matrix of n by n is equal to 5 and choose the relatively simple input of x. The matrix A is this and input of x is this. Then we will get the output of x, and output of x will be in the following form. Clearly, for any input of x, we can evaluate the unit output of x. Therefore, the first two head mod conditions are satisfied. To test the stability condition, we can define an additive noise vector n that is satisfy small to form x dash input of x dash. Evaluating output of x gives input of output of x dash, the matrix this is equal to this, and we will add some data and we will get the output of x dash. We see that output of x dash is close to the nominal solution of output of x. Formally, we can define the relative magnitude of the input and output error to provide the measure of stability. Input of x dash is equal to A output of x dash. We use the inverse matrix. Inverse matrix that will given by this matrix. Again, using 10,000 different noise vectors, we obtain the distribution of S for this reverse problem. Notice the x-axis is scaled by 10 raised to the power 5, meaning that the relative error is greatly amplified. To evaluate, suppose we rounded output of x to 3 decimal places and then evaluate input of x dash x. Then we will get output of x dash is equal to transpose of this matrix, and input of x dash is equal to A inverse output of x dash transpose of this matrix. In the reverse problem, we can not even tolerate rounding error as input of x dash bear no resemblance in input of x at all. Therefore, this problem fails to satisfy the head mod third condition and is therefore ill-posed. Because of ill-posedness, this is inverse problem or reverse problem. Therefore, it is not simply a question of semantics, but there is a fundamental distinction between the forward and inverse problem. Even if had first defined the operator B is equal to A inverse and we went to through this same analysis, we would still conclude that B is the inverse problem and B inverse is the forward problem objectively based on the stability creation. In simple words, we can say that a problem which is not well posed is known as ill posed. If one of two problems which is inverse to each other is ill posed, we call that is inverse problem, and other one is the direct problem. The theory of the inverse and ill-posedness problem is also widely used in solving applied problems in almost all fields of science and technology, and particularly in physics. It is used in astronomy, quantum mechanics, electrodynamics, etc. And geophysics also, seismic exploration, electrical, magnetic, gravimetric prospection, logging, magneto, sounding, etc. In medicines, we can use the inverse problem in X-ray, NMR tomography, ultrasound testing, etc. In ecology, we can use the inverse problem air and water quality control, space monitoring. In economics, we can use also the inverse problem optimal in optimal control theory, in financial mathematics, etc. And in this is also used in mathematical model to find the rate of infection and rate of transmission, number of susceptible person, number of infected person, and other parameters. The scientific procedure to study the physical system can be divided into the following three steps. First step is parameterization of the system. First step is parameterization of the system. Discovery of a minimal model parameter whose values completely characterize from a given point of view. Next step is forward modeling. Discover of the physical laws allowing us for given values of the model parameter to make predictions of the result of measurement on some observable parameter. And the third step is inverse modeling. Inverse modeling, use of the actual result of some measurements of the observable parameter to infer the actual values of the model parameter. These are the three steps to find the inverse problem. In figure, we can find if model M is given, and we can find the data using the physical model. Then this is known as inverse problem. And if we know the data and we have to find the model, this is known as the inverse problem. Next, in input and output terms, if we give the input signal and use physical system, then we get the output signal. But this is the forward model, and if we get output signal and we have to find the input signal using the physical system, then this is known as the inverse problem. Inverse problem use basically I use the inverse problem in epidemic models. There I using the SEIR model to describe the inverse problem and to find the parameter. The first of all, I introduce the SEIR model. The term S, it means susceptible individual. The term E, exposed individual. The term I, infected individual, and the R is used to recovered individuals. And the equation for susceptible is this, exposed for this, and infected for this, and recovered for this. In this model, we will discuss the conformable fractional derivative used to find the inverse problem and get the result of treatment, after treatment and before treatment. We will convert this model into conformable fractional derivative, and the model will be in the form t raised to the power 1 minus alpha s dash b raised to the power alpha minus beta raised to the power alpha. We convert this model into conformable fractional derivative. And this alpha means the derivative power of the derivative will be in the decimal form. And these are the initial condition. S naught is equal to small s naught, E naught is equal to these are, and these all are real numbers. Now we will optimize the problem and get the equality constant with the initial condition. And now we will use this equality constant in our previous model, which is conformable fractional derivative model, and use the Grunwald-Lutnikov fractional derivative approximation formula to solve this conformable fractional derivative optimization control problem. After using these formulas, we get the parameters b is equal to this, mu and nu is equal to 1, and these are the initial values. And now we will take the derivative power of the derivative is equal to 0.5 and beta is equal to 10 and Q is equal to 0.86146, and we have to find the treatment rate before uh, before treatment. This value is showing in the graph is susceptible, number of susceptible, this is number of exposed, and this is number of infected person. This is after treatment. Before treatment, we get the number of exposed person, number of infected person, number of susceptible person, and number of recovered person. We are clearly find that after treatment, after treatment, number of exposed and infected person are decreasing. When the number of exposed and infected person will decrease, then they cannot infected other person. It means infection will not spread. Next, our next model is SEIR model. SEIR model. This model is for Zika virus. In this model, as we use the same model. SEIR model is for human, and SEIR model is for mosquito. Because mosquito population also infected. If one mosquito is infected, then that will be infect the other mosquitoes. Here the terms use SH mean human susceptible individual, E human exposed individual, IH means human infected individual, RH means human recover individuals, and SM mosquito susceptible individuals, mosquito exposed individual, IM means mosquito infected individuals. These are the models for human and for mosquito. We will convert this model into the Caputo fractional derivative with the classical integer model. We will convert the previous model into Caputo fractional derivative, and the model will be in this form, where alpha is the power of the derivative. We will put these values in terms of fractional in the form of fractional. Next, now we will consider this model into conformable fractional derivative. The same model convert into the same integer model convert into Caputo fractional derivative, and again convert into conformable fractional derivative. And now compare these three: classic conformable fractional derivative, Caputo fractional derivative, and classical derivative after using these parameters: alpha transmission rate for human, alpha m transmission rate for mosquito, gamma recovery rate, beta infected rate for human, beta v infected rate for vector. These are the parameter. After using these parameter, we get the graph. This is for classical derivative, this is for conformable derivative, and this line is for Caputo derivative. But in the this is for 50 almost 0 to 50th week. But in the last 48 to 50th week, we consider that we get the same values of the model with the classical derivative, with the conformable model, and with the Caputo model. Now we can use inverse problem in many other fields of the science and technology. Like that, this is the original data, and after the process we get the observed data. This is direct problem. And if we get the observed data, then can we find the data restored, which is almost resemble to the original data? This is all inverse problem in image. Next, attempting to understand the sustainability complex phenomena and solve a problem such that the probability of error is high is usually arrive and stable ill-posedness problem. Indeed, everyone realizes how easy it is to make a mistake when reconstruction of the past from a number of facts of the present. For example, to reconstruct a crime scene based on the exciting direct and indirect evidence. Next is determine the cause of disease based on the result of a medical examination and so on. Next, the same is true for tasks that involve predicting the future. Next point, predicting a nature disaster or simply producing a 1 week weather forecast or reaching into incredible zone of explore their structure. Next, examination of patient brain using NMR tomography. Inverse problem you can use also in these fields. Next, classification of the inverse problem. The inverse problem is said to be retrospective if it is required to determine the initial condition. Second point, the inverse problem is called a boundary problem if it is required to determine the function of the boundary condition. Third, the inverse problem is called the continuation problem if the initial condition are known and the additional information and the boundary condition are specified only on the certain part of the boundary of the domain and it is required to find the solution. The fourth point is the inverse problem is known as source problem if it is required to determine the source. Last but not the least point is the inverse problem is called the coefficient inverse problem or inverse medium problem if it is required to reconstruct the coefficient of the main equation. These are the classification of the inverse problem. Again, we can use the inverse problem. Acoustic problem. Inverse problem we can use in acoustic problem when we want to compute the source which is responsible in the field of acoustic. Here the acoustic field is measured near to sound source and the problem is to find the acoustic field of source of surface. In the current project, we use the formulation based on the integral equation formulation and involved to describe the source surface. When this integral equation is described, it leads to a linear system of equation with a large, dense, and ill conditions coefficient matrix. This system is done in solved by the minimum of appropriate discrete regularization algorithm. Now, this image, we will create this image. The microphone array used to measuring the acoustic field is seen to be left of the tire and the location of the loudspeaker is shown by the red arrow. The goal is now to record the vibration of the tire generated by the loudspeaker from a measured acoustic field, which is shown in the figure. Again, last, if a person standing in a sunlight or light, then we will get the shadow. This is the direct problem. But if the shadow, we have the shadow, can we find the structure of the person? This is the inverse problem. So there are lot of area which we can use the inverse problem to find the many other parameters and lot of scope to find various field of science and technology to get the parameters with the help of the inverse problem. So, thank you.